Hello, everyone. I hope you're all well and safe and healthy and able to stay on top of your schoolwork. In this lecture, we're going to continue on the theme of electrochemistry. Last week, we went over balancing half reactions and splitting it up into an oxidized and a reduced reaction, and then adding hydronium ions as necessary, electrons to balance it out, and then stitching those reactions back together. I want to start off this lecture by doing another one of those problems just to have a review before we kick it into reduction potential. Reduction potential is similar to potential energy, but instead of looking at it in the context of potential energy being dictated by how high something is, with reduction potential, we're looking at the measurement of current, or how electrons are going to move in between these two half reactions. Okay, so let's share the screen and get started. So the one that I want to go over is this problem. It is slightly different. It was on the slide deck from last week that I just didn't go over. I said, you guys work on these at your own time, and if you had any questions, let me know. The reason I wanted to go over this one in particular is because it is talking about something that is oh goodness, there we go. It's talking about something that is a basic solution right here, see? Okay, so when you're balancing basic solutions and you end up having to add hydronium ions, by definition, that's going to be an acid-base reaction, right? And so we will have to add one extra step into that process, right? And so remember, to start off with these half reactions, you have to assign oxidation states and then separate them into the two halves, one being oxidized, one being reduced. And then you balance everything except for the hydrogens and oxygens, and then you balance those. And then you can balance the oxygen by adding water. You can balance the hydrogens by adding these hydronium ions. But in this case, if we add hydronium ions, we need to neutralize them by adding hydroxide ions, okay? So I'm going to write a little bit of stuff on the board for you guys and then show you how to do this. Okay, so here's that reaction again. And the first thing we have to do is determine what's being oxidized and what's being reduced, right? So we can start off with iodine here. It has a negative charge, so it's an ion. And because it falls in group 7, we say that that charge is going to be the -1, right? Over here, this is I2. So that's essentially thinking of iodine in its elemental form, and things in their elemental form have no charge, or no oxidation state. And so essentially you're going from a -1 to a 0. So that is going to be oxidized, right? So we can write I negative going to I2. Now MnO4 now becomes MnO2. And we know that with MnO4, we've done this several times, the manganese is going to be a +7, and the oxygen is going to be a -2. And in this case, oxygen is -2, and manganese is +4. So the overall result of that is that it's being reduced, right? It's cumulatively, we have +7 minus 2 is 5, +4 minus 2 is 2. So it's gaining electrons to drop it down from 5 to 2. And as a result, that is being reduced. So M4 2. Right? So what's the first thing we do? We need to balance these. So let's balance our oxidized reaction. There are 2 iodine here, just 1 there. So let's put a 2 here. Okay. Now that's balanced from the perspective of mass. For a reduced reaction, we need to do a couple things first. We'll need to add water over here, okay? So and in order to do that, we'll need actually, I think we'll need 2 of these, right? Because we have 4 oxygens here and 2 here. So let's make this 2. And that gives us, let's see, that gives us 4 oxygen. But now we have 4 hydrogens on this side. So we need to put 4 hydrogens here as well. Okay. Now everything should be balanced, right? So if we write this out again, I'm going to erase this now. That becomes 2I goes to I2, and then 4H plus goes to okay, good so far. Now, these hydronium ions are we're going to have to neutralize because this is a basic solution. So how do we neutralize these 4? Well, we add another 4 hydroxides. Because what does 4 hydronium ions and 4 hydroxide ions make? Well, they make 4 waters. And so what we can do is we can now combine this and erase this now. And just turn those 4 hydronium ions and 4 hydroxide ions into 4 waters. Okay, great. Now, what's the next thing we have to do? We have to add on electrons to balance the charge, right? And so for this one, we'll need to add 2 electrons, right? Because there are 2 iodine ions here. So 2 at a negative charge is a -2. This is 0, so we put 2 here. Okay. And then similarly, we're going to need to add 3 electrons on this side to balance that out. Because remember, the difference up here is 5 and 2, right? So we add 3 down here to bring this charge down to balance out with the 2 oxidation state here. All right. And then next, we need to essentially balance those electrons, right? So we have 3 on this side, we have 3 here, and we have 2 here. We need to balance them so that they're the same, so we can essentially cancel them out later on. So 2 and 3, you multiply them together, you get 6, right? So that's what they share. So let's multiply everything in this top reaction by 3 and everything in this bottom reaction by 2, okay? So we multiply this by 3, by 3, by 3, and we multiply this by 2 times 2 times 2 times 2 and times 2. Okay? So if we multiply everything by 2, now we get, what is this, 2 times 3? That's going to be 6. 3 times 1, that's just going to be 3. 2 times 3, 6. That's good. And then this, 4 times 2, that's going to be 8. 2 times 1 is 2. 2 times 1 is 2. 2 times 2 becomes 4. And 2 times 3 becomes 6, right? Cool. So now we say, what cancels and what can we reduce? Well, we can say that these 6 electrons cancel, right? So these 6 up here cancel out with these 6 down here. And let's look at the waters. We have 8 waters on this side, and 4 waters on this side. So if we divide both sides by 4, that's going to cancel out that water entirely and reduce this down to 4. Okay. And then I forgot to add the hydroxides on this side. Remember, we added 4 hydroxides on this side to neutralize those hydronium ions. You also have to do whatever you do to one side, you have to do the other. So we have 4 over here, 4 hydroxide ions. And then we all have to multiply those by 2 as well. So we end up with 8 hydroxides. And that does it. We put it all together. What do we get? Black. We get 6 iodine plus 4 H2Os plus 2 MnO4. I think that's it. Yields 3 I2 plus 2 MnO2 plus 8 OH. Okay, pretty simple. Hopefully you already did that problem and got it right. You may not have known to add the hydroxide, which is why I wanted to go over that. But that is the answer. That's how you balance that. Okay, let's share the screen again. And the next one is another half reaction method that I want you guys, if you didn't work on this one last week, to give it a try this week. Because again, like I like to say, practice makes permanent, right? Doesn't make perfect. If you're practicing it the wrong way, you're not going to be perfect. You're going to be imperfect. So practice makes permanent. Make sure you practice it the correct way. And that way, when you have to come up with the answers on a test, you'll do it the correct way. I believe this one came out of the OpenStax textbook, so it should have the answers to it, walk you through it, give it a shot, and then check it out in the book. Here's another one too. Maybe this is the one that's in the book. One of them's in the book. So, okay, that brings us to reduction potential, okay? And like I said at the very beginning, instead of looking at potential energy by height, so if we have a waterfall, there's going to be high potential energy at the top of the waterfall, and it's going to get less and less as it approaches the bottom. Instead of looking at it like that, we look at the movement of electrons between half reactions as reduction potential, the potential for something to be reduced, right? And so this is going to be broken down into the context of voltage or cell potential. And that is what we use to study voltaic or galvanic cells, right? And that is what we use to look at the difference in the reduction potentials between two half reactions. What are we doing with this? We're looking at current, really, just the movement of electrons and how many of them are moving. And for spontaneous reactions, the potential, the cell potential, is going to be positive, okay? Why? Because electrons want to go to a positive, right? And spontaneous, as we learned last quarter in thermodynamics, spontaneous reactions occur without outside intervention, right? They're kind of like duh reactions or common sense reactions, right? In a way, you can think of it that way if you want. So luckily, most of the reduction potentials for these redox reactions have already been determined and figured out. And so I've listed several different tables because the one in OpenStax isn't all inclusive, like most of the tables in OpenStax. So I have some additional supplementary tables that I've found from other texts to add to this slide deck in case you come to problems where you have to look up reduction potentials and you go to your table in OpenStax and it's not there. Okay, so these are the ones in OpenStax, table 16.2. Like I said, I was working on some reactions and found some that were not in this table. So here's another one here that's kind of blurry. Sorry, I tried to get as best I could, but essentially it gives you still these half reactions, and what you're looking at is the this E degree. This is measured in volts. That's the voltage essentially of these half reactions. Okay, and that's what we're going to be using to figure out these reduction potential equations. Now, just like with potential energy, and the higher something is, the greater the potential energy is going to be. the greater the difference between two reduction potential values, the greater the voltage of the overall cell, okay? So what that means is that the greater the difference between this number, this 0.34 on this half reaction, the greater that difference is between this number, this negative 0.76 on this half reaction, the further away they are from each other, the stronger the electrons are going to want to move away from one end to the other, and the greater the overall voltage is going to be, right? So the closer these values are to each other, the lower the voltage is going to be. Now, when we look at voltaic cells, most of the time they're going to occur in separate containers or separate spaces, right? This is one of the most simple examples of a voltaic cell, where we have a zinc strip put in a solution of copper ions, okay? Now, in spontaneous redox reactions, electrons are going to be transferred, and energy as a result is going to be released in a spontaneous redox reaction. And what happens in this particular redox reaction is that zinc is immersed in this copper ion solution, and the zinc atoms are going to transfer electrons to the copper ions, okay? So they are going to transfer these electrons right here, 2 electrons out of this zinc strip. And what those electrons are going to do is now they are going to reduce the copper from a copper ion with a 2+ charge to just a regular old copper atom, right? So the zinc is being oxidized, the copper is being reduced, and as a result of that reduction, it's going to deposit onto the electrode here. So you can see that there is this, this deposit of copper on that strip, which this may look familiar to you based on the lab we did last quarter. Okay, so that's a simple voltaic cell, as like I said, as simple as it gets. But what if we have oxidation and reduction half reactions that are separated from each other? What's going to happen in that case? Trying to move something out of the way. Okay. Here we have 2 beakers, and let's say we have the oxidation half reaction on the left side and the redox half reaction on the right side. Can the reaction proceed? Well, what they're saying is, can the electrons flow from the oxidized half reaction to the reduced half reaction? The answer, of course, is yes, but the circuit has to be closed. It depends on the apparatus that's set up, right? So if the 2 half reactions are separated, electrons must move from the oxidized half to the reduced half, okay, by having some kind of conduit connecting them. So in this case, this is going to be, this is copper and zinc, and now instead of being in one beaker, they are separated, and there's this cable that's connecting them to this voltmeter. And then they have this little thing down here called the salt bridge, which we'll talk about in a minute. But just like it moved, just like in this previous, situation where they're in the same container, we have it going from the oxidized zinc to the reduced copper. That situation has to be true also when they're separated physically. It has to move from the oxidation half reaction to the reduced half reaction. This, by definition, is a voltaic or galvanic cell. And again, the electrochemical cell that produces this electric current comes from a spontaneous chemical reaction, okay? It happens naturally. Later on, we'll talk about electrolysis, and that's going to be kind of the opposite. That is going to be when electrical current isn't produced, electrical current is consumed. And that's going to then drive a non-spontaneous chemical reaction. Okay. So if we looked at this, if I asked you, which direction will the reaction proceed? Will it go from the copper strip on the left to the zinc strip on the right? And if I asked, what is the standard cell potential of this reaction? Hopefully, by the end of this lecture, you'll be able to answer these questions, okay? Which direction will the reaction proceed? Well, let's move on. This is the same, basically the same setup in a more realistic form. In this voltaic cell, we have the zinc, which is going to be considered the anode, and the copper, which is going to be considered the cathode. Now, the reason they're called this is because there is this salt bridge here that I mentioned. This is what essentially balances the charge, but also closes the circuit, right? Think of this as a circuit, and it's going to close the circuit and allow the electrons to pass through from one side to the other. And this is called the anode because the anion flows to this side. Okay, in the salt bridge, the anion goes here. So this is the anode. Whereas on this side, the cation, in this case, it's sodium because they have added sodium nitrate for this salt bridge. The anion is, or the cation is flowing to this side, so we call this the cathode, right? So movement of cations, movement of anions dictate the names that we give these sides. Oxidation occurs at the anode, reduction occurs at the cathode, okay? So oxidation, remember what we talked about in that first voltaic cell when they were together, we said that the zinc was oxidized and the copper was reduced, okay? So zinc is anode, and that's where the electrons are going to start. They're going to flow from the anode and make it over here to the cathode. And in this scenario, I think, yeah, that's right. Okay, salt bridge, I mentioned that. All of this is going to be used to calculate cell potential, okay? The difference in the electrical potential between two dissimilar metals that end up being connected in this circuit here, okay? It's the driving force of current in a redox reaction, all right? So going back to this question here, which direction will it proceed? Well, based on what we just learned, it's going to proceed from the zinc here on the right over to the copper on the left, okay? Now, there's another way that we could kind of easily determine this just by looking at this E degree value. This is kind of this is the cell potential, if you will. It's negative 0.74. And over here for copper, it's positive 0.34. So again, if it's a spontaneous reaction, it's going to want to go away from a negative charge and over to a positive charge or a less negative charge. If both of them are negative, it's going to want to go to where to whatever side is less negative. Okay, so that was kind of a little bit of a clue, a little bit of a hint um, going into this. Here's basically the same diagram, only instead of being connected to a voltmeter, it's connected to a light bulb, and bling, light bulb goes on because there's electricity flowing through it. And I think a couple other different, there's salt bridge is potassium nitrate instead of sodium nitrate. And it's kind of showing you again this cartoon of what's actually going on with the zinc and the copper. So whichever one you like better. I just wanted to give you several different examples. And then this is lots of text, but I'm not going to go over this. In case I missed something or you didn't catch it, I always like to provide kind of a summary for those of you who learn better by visual reading of something rather than just listening to me talk. Okay, so you can go over that if you want. But basically, the major points to focus on is that oxidation occurs at the anode, reduction occurs at the cathode. Okay, and the electrons are going to go from the anode to the cathode. All right, so potential difference. Potential difference is the measurement of the difference in potential energy. This is going to be measured in joules per unit of charge, which we measure in coulombs. All right. So if we're looking at the international standard units of potential difference, we're going to say, is the volt or the V being equal to 1 joule per coulomb? All right. And since the potential difference can lead to a force that will cause electrons to move, we also refer to this as electromotive force or EMF. Okay, so several different ways of calling the same thing what it is, right? Potential difference, electromotive force, and essentially, just like water is going to flow downhill, right, in response to gravity, and that gravitational potential energy, electrons are going to flow through some kind of conductor, right, in response to an electrical potential difference. Okay, this potential difference is analogous to potential energy. Okay, and it's going to have a net effect of creating an electrical current. And remember what I said before, the more different these ends are from each other, the greater the volt is going to be. The greater the volt, the greater the energy per unit of charge. Okay. Now, another name, because, why not name these things a bunch of different things? We can call potential energy cell potential, okay? Potential energy is cell potential when it is being measured in between two electrodes. So we can call it cell potential or E cell, or we can call it cell EMS or cell electromotive force. When the E cell or the EMF are at standard conditions, we call them standard cell potential or standard EMF. So what are these standard conditions? Well, the same standard conditions we usually talk about. One molarity concentration for reactants in solution, 1 atmosphere for gaseous reactions, and all of it's going to be at 25 degrees Celsius. Okay. So we look at this reaction again, this zinc and copper, we can say that that has a standard cell potential of 1.10 volts, okay? Meaning the difference between those two half reactions is going to equal 1.10, okay? Now, how do we calculate standard cell potentials? Again, as I said, electrons travel from the anode, and the anode is where oxidation is happening, to the cathode, and that is where reduction is happening, okay? So we define the standard cell potential as the difference in voltage between the cathode, or the final state, that's where the electrons end up, and the anode, or the initial state, where the electrons are being released, okay? So standard cell potential equals E final minus E initial, or another way of putting it, E cathode minus E anode. Now, we are limited because we can't actually measure electrode potential in a half cell directly, okay? We can only measure the overall potential that occurs between two half cells when they're combined into a whole cell, right? So what we do to work around this is that we arbitrarily assign a potential of 0 to some particular electrode of a half cell. And in this case, it's going to be what we call the standard hydrogen electrode, or She. Okay, and that is this down here. 2 hydronium ions plus 2 electrons give us hydrogen gas. Okay, we're saying that that is going to be our 0. So everything else, all these other half reactions, are going to be measured and assigned a value in relation to that She, that standard hydrogen electrode, being 0. Okay. And so in this case, we can say that this She, this 2 hydronium ions plus 2 electrons give us hydrogen gas, is going to be the E cathode, okay, because it's on this side, and we're saying that the standard hydrogen electrode is on the cathode side, and that's going to be equal to 0. All right. Now these are hooked up to a voltmeter, and it's saying that the overall net voltage is 0.76. Okay. So our cell potential, our standard cell potential, is 0.76. So really all we need to do is find the E of the anode, right? And so how we could set that up is we could say, let's write it out here. We could say that 0.76 volts equals the cell potential of the cathode, which in this case we said is 0, minus the cell potential of the anode. Okay. And so essentially that's going to be a negative 0.76, right? And if we did the math there, that would be equal to negative 0.76. Okay, so that is how we calculate standard cell potential. Clear this up. we just look at the cell potential, the standard cell potential values of our cathode and anode, or our oxidation and our reduction half reactions, and we subtract them from each other, and that will give us the overall standard cell potential. Okay. So try that, okay? What you're going to do for this reaction here is you're going to use that chart in OpenStax, I think table 16.2. And if you can't, if some of them are missing, look them up in the other tables that I included in this slide deck and see if you can figure this out. What do you got to do? You got to determine which species is being oxidized, which species is being reduced. And then once you have that figured out, all it is simply looking up the cell potential values for those. Okay, so I'm going to pause it here and give it a go. See what you can come up with. Okay, so first step, we have to determine which species are oxidized, which are reduced. And so let's start with aluminum. Aluminum, in this case, is in its elemental form, so it's going to be 0. It's going from 0 to 3 plus, okay? So it's losing electrons, so it's going to be oxidized. That's what's oxidized. So we have our L going to Al3, and then we usually write it with 3 electrons to balance it out, right? So 3 plus 3 electrons, and then neutralize it so this is balanced, okay? So that means that the NO3 plus 4H plus 2 plus 2H2O. That means that this is our reduced reaction. And so we have to tack on, we usually tack on 3 electrons here as well. Why? Because they'll end up canceling out in our balanced half reaction method that we talked about. But what's a -1 and 4 positives? Positive ones, that's going to be a net of 3 plus, right? 4 hydronium ions is going to have a charge of 4 plus, because there's 4 of them, minus this 1, so plus 3. So we had 3 electrons here to balance that out, okay, because there's no charge over here. So that's our oxidized, that's our reduced. Now we have to look up these values for these reactions, okay? So let's go. Here's OpenStax, and here's table 16.2. And so I'm looking for aluminum. I probably need to share my screen, don't I? There we go. There we go. All right, so I'm scrolling down. Here it is, right here. Okay. And that's going to be a negative 1.662, okay? And then let's find our other reaction, nitrate. Okay, well, shucks, it's not here. So, okay, case in point, this is an example of it not being here. So, oh, it says sharing is paused. I don't know if I'm sharing or not. Let's try sharing it again. Okay. So in this case, let's go back. Let's go back to, sorry, blah, 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 blah. Oh, I'm going the wrong way. Let's go back, sorry, to the table. Is it here? Is it here? Here, yes, right here. Plus 0.96. Okay. Let's go back to our reaction. This one. Yes. Okay. So what is our anode? It's the oxidized reaction. Our cathode is the reduced reaction. Okay. So I wrote down these values here, negative 1.66 and positive 0.96. And so what does E cell equal? We said it was E final minus E initial, or E cathode minus E anode. Okay, so this value is for the oxidized, and this value is for the reduced, right? So we say that it is equal to 0.96 minus the negative 1.66. So that should be, that's a negative, no, it's a positive 2.62, I think. I don't have you guys here to double check my math like I'm used to. I miss you guys. I think it's 2.62, something like that, off the top of my head. So that is the standard cell potential. That's how we calculate it. Let's go back to this. So here's the next problem. Give it a shot. I'm not going to go over it. If you get stuck on it, let me know during lecture tomorrow, which I guess might be lecture today for you guys. I'm recording this. It's Monday night. Anyway, let me know during lecture and we can go over it, but it's basically the same thing. You just split it up into the oxidized half reaction, the reduced half reaction, then look up the values and subtract accordingly. Okay. What's happening? Okay, so that's that one. Here's another sample problem, same kind of thing. They've already broken it down into half reactions for you and given you the volt values, so that's pretty simple. Now, predicting spontaneous reactions. We can predict whether or not they're spontaneous based on the way that they're arranged, okay? So again, it's going to be spontaneous if it goes from what? From the oxidized half reaction to the reduced half reaction. And that direction, those values have to be such that the reduced value is less or is more than the oxidized value, right? The oxidized value is less, then the electrons aren't going to want to flow, right? They want to go to a more positive situation. So in these two, what I want you to do is to break them down into find out which one's reduced, which one's oxidized. Is the magnesium or the iron being reduced? or oxidized, and then look up those values and see if that makes sense. See if a spontaneous situation would allow that to occur, or if it would have to be non-spontaneous. Okay. Okay, so here's the reaction here. And like I said, we have to determine what's being oxidized, what's being reduced. And I've left out their states, whether it's solid or aqueous, just because I'm dealing with a much smaller whiteboard, so I'm just trying to save space. I always thought the whiteboard in our chemistry classroom was small, but a good example that things can always get worse, right? So appreciate what you have. Anyway, what's being oxidized? Well, what's being reduced, what's being oxidized? Let's look at iron. Iron here is going to have an oxidation state of 0. And then over here, it has oxidation state of +2, right? So 0 and +2. So in order to go from 0 to +2, it must have lost electrons, and therefore it's going to be oxidized, right? So Fe goes to Fe2 plus, and then again, we usually write 2 electrons to balance it out. Therefore, the magnesium must be reduced, and it is, because it's going from an oxidation state of +2, it's the reverse, right, to 0. So it must have gained electrons in order to go from +2 down to 0. So Mg2 plus 2 electrons gives us Mg. Yeah, that looks kind of legible. Let's look up these values and see if it makes sense. Okay, so here's the table. We're going to look for magnesium, magnesium ion going to magnesium solid, and then solid iron going into aqueous iron. So let's look. Here we go. Here's iron. That's 0.7. Oh wait, no wait. That's iron 3 plus. Here it is. Okay, right there. So iron 2 electrons going to solid iron. That is a -0. Let's do red. -0.447045. We'll just say volts. And that's for iron. And let's see here. Maybe we'll luck out and get magnesium also on this same table. Bingo. Okay, that is right here. -2.372 volts. Okay, and that's going to be for our reduced, and the 0.45 is for our oxidized. So this is what we come up with. We have a -0.45 for our oxidized and a -2.37 for our reduced. Now, what is the direction that the electrons flow? From the anode to the cathode. What's the anode? The oxidized reaction. What's the cathode? The reduced reaction. Are electrons going to go from something that's -0.45 to something that's more negative? No, that's not going to be spontaneous, right? It's going to want to go from something that's negative to something that's positive, or something that's at least less negative. So Is this reaction spontaneous? Nay, it is non-spontaneous. Okay, so that was A. Try B. Now that we've done that, I'm going to pause it. You do the same. I'll write it up. Try it out, and then we'll go over it together. Okay. Okay, so like with A, we need to determine which is being oxidized, which is being reduced. And so let's look at iron here. Iron is going from an oxidation state of 0 to +2. So in order for that to happen, it must have what? Lost electrons. And so therefore it's going to be oxidized. So Fe goes to Fe 2 plus 2 electrons. Hopefully that looks familiar. And then therefore, if we look at lead, it's going from a +2 to a 0. So it's going down. So it must be gaining electrons. Therefore, it's reduced. So lead goes lead plus 2 electrons, right? Yields lead. So now we just look up the values for these half reactions. Share screen. Let's go to that table. Maybe we'll look out and they'll both be here. We already know one. We already know that. Yeah, we already know this one from A. So that's negative 0.447. -7 for our oxidized. Okay. And then lead. Is it not here? Ah, is that it? Yeah, that's it. Here it is. Okay, so that is a negative 0.126 for reduced. Okay, so again, it's going to go from our oxidized anode to our reduced cathode. And when our oxidized anode is a negative 0.447 going to a negative 0.126, it's not going from negative to positive, but it's going from a higher negative to a lower negative. And so that is going to happen spontaneously. So that is an example of a spontaneous reaction. Here's another example. I'll let you guys, I won't go over this. Same applies for this as the other ones. If you have any hiccups, feel free to ask me during lecture or lab time. I believe this came from OpenStack, so it should walk you through it. Give it a shot, and hopefully it's not too challenging. All right. So what is the relationship between G and E? I think I skipped yeah. You remember the G is Gibbs free energy, right? And when conditions are normal, we can use delta G to derive the spontaneity. and equilibrium conditions, right? So if we have nitrogen and hydrogen on one side, and that forms ammonia on the other side, at certain states, you're going to have pure reactants and pure products, right? But at some point, they're going to want to go into equilibrium, and we can measure that in terms of the amount of free energy, right? Once we get to the point where Q equals K, delta G is 0. A little review from last quarter. We can use this also to look at spontaneity of redox reactions, okay? So if a redox reaction is spontaneous, it's going to proceed in the forward direction. So reactants are going to drive into products, and that's going to be, of course, assuming that everything is under a standard state. But when that's the case, G is going to be negative. The cell potential is going to be positive, greater than 0, and K is going to be greater than 1, okay? Equilibrium constant. When these reactions are non-spontaneous, it'll proceed in the reverse direction, okay? And so it's going to go toward a more reactant-favored side, and that is going to be kind of basically the reciprocal of a spontaneous redox, where G is now going to become positive, and cell potential and K are both going to drop down, right, below 0, or below 1 for K. When we apply Gibbs free energy, or the change in that free energy, to a redox reaction, we can use this equation here. Delta G equals NF cell potential, okay? Well, what is that? N is going to be the number of moles, and F is going to be a constant. It's going to be called the Faraday, which if you're not familiar with Michael Faraday, I recommend you Wikipedia him or something like that. He came from basically an impoverished background with no formal education, and was just so brilliant and self-motivated that he taught himself science and how it worked, and came up with electromagnetic force and all kinds of great things. So it's a very interesting story. Anyway, off that sidetrack, what is F? F is a constant that is equal to 96,485 coulombs per moles of electrons, okay? Or we could write that as 96,485 joules per volt times mole, all right, here, okay? So that is what we have. We basically have a constant for F, and then the moles in the equation, and whatever that tabulated value for cell potential is. And we use those, we can calculate the free energy. Or if we have the free energy and missing one of the other ones, we can solve accordingly. Let's clear my doodles and go to the next slide. Okay, so use the tabulated electrode potentials, or cell potentials, to calculate G for this reaction. Okay, remember, go back if you need to look at this equation. You already have the Faraday constant. You have to look at the coefficients to figure out what your moles are going to be, and see if you can solve this. Okay, we'll pause it and see what you come up with. Okay, so once again, we need to break it down into oxidized and reduced half reactions. So we have its elemental form going into its ionic form. So 0, and essentially it's going to be +2, and then here it's going to be a -2 and a 0. So what's being oxidized? Well, this is going from 0 to a +2, so it must be losing electrons, right? And so therefore it's going to be what's oxidized. 2 goes to 2I minus plus the 2 electrons, right? Oh, no, that'll be balanced here. That'll be I2 plus 2 electrons goes to 2I minus, right? There we go, that's better. Bromine is going from a -2 to a 0. So it must be, oh wait, I think I messed that up. 0, it's losing electrons to get to there. Here it's gaining electrons. That's yeah, I guess that's right. Yeah, okay. See, even I get confused with this sometimes. This is oxidized, so 2Br minus plus, or no, yield. I've got this. No, I've got this wrong. Take 2. So we have it going from 0 to, now I know what screwed me up. I put that as a +2. That's a negative. So it's going from a 0 to a -2. So this must have gained electrons, and therefore it's going to be reduced. So I2 plus 2E yields 2I minus. There we go. And here we go from -2 to 0. So it's lost electrons to gain that that overall charge of 0. So that's going to be 2Br minus goes to Br2 plus 2E. There we go. Okay. So what was our equation? We said delta G equals a negative moles. It's going to be the moles of electrons. So these guys here times F times these. Oh man, that's terrible. E times the cell. God, that's even not much better. Times the cell potential, right? Okay. So a little bit here. We also need to look up the values, right? To determine what this E cell is. And so I've already looked these up, but they should be in that table either in OpenStax or what I gave you in the slide deck. And so what we have for our oxidized, just write O for short, our cell potential for this oxidized reaction is going to be 1.09 volts. Okay. And for our redox reaction right here, it's going to be 0.54 volts. 0.54 volts. Okay. And so remember, it's going to be the reduced minus the oxidized, right? Or final minus initial. And so we got to figure out what the other things are, okay, to solve. Say that delta G, maybe this looks better. Delta G is equal to a negative N. Well, in this case, it's 2, right? And they'll end up canceling each other out, but that is the number of mole electrons. It corresponds to the number of electrons that are canceled in these half reactions, all right? So we can say that's a -2 times the Faraday constant, which is 96,485. 96,480. Oh, well, I should include my units. 2 moles of the electrons, okay, that are being transferred, times now the 96,485. In this case, it's coulombs per moles of electrons. Okay. And then we multiply that by the E cell, or the difference of these two, which is a -0.55, -0.55 joules per coulomb. Because remember, volts equal 1 volt is equal to 1 joule per coulomb. And so it's getting hard to see. Sorry about that. Maybe it's the marker. Let's move over here. That's better. Okay. Joules per coulomb. All right. So a -2 times our F constant, 96,485 coulombs per moles of electrons, times the difference in our values here that we looked up for our cell potential, and all of that should equal delta G, should equal a positive 1.1 times 10 to the 5th, 1.1 times 10 to the 5th joules. Why joules? Well, that's simple. Moles of electrons cancel, coulombs cancel, and the only unit we have left are joules. So we haven't been working with units much, with equilibrium and Ks and Qs and what have you, but once we get back to free energy, they become relevant again. Okay. So that was that problem. What is now the relationship between cell potential, standard cell potential, and equilibrium constant? Well, we've just said that delta G is equal to negative moles of electrons times Faraday's constant times essentially the standard cell potential. And you will remember from last quarter that the delta G is also equal to a negative R constant, the gas law constant, times temperature. And this is going to be standard, right? So 25C, or in this case, 298.15, times the natural log of K. So if we take those two reactions and put them together, we can say that we could say that this is equal to this if they're both equal to G, right? So this equation that we just learned is equal to this equation that we learned last quarter, okay? And so therefore, the standard cell potential, if you just rearrange things a little bit, is equal to this initial Gibbs free energy reaction divided by the moles of the electrons times Faraday's constant. And when you divide this negative by another negative, you get a positive. So we get rid of our negatives that way, okay? Now, when we put it all together, we end up with 0.0592 volts over N times the log of K. And so how did we get to that? Well, first, we know that the R constant, right? R is equal to, probably be better if I just type it, 8.314 joules per moles times Kelvin, right? And we know that T, bad T, is equal to, this is standard conditions, right? So it's going to be 298.15 K. And we know that F, move this out of the way. We know that F it's through my little window at the now. I can't see my window. That's still stubborn. Sorry, there we go. F, all that for just this. F is equal to 96,485 coulombs per moles of electrons. Okay. And so that's good. The only thing now that you might notice that looks funny is that we went from natural log of K to log of K. And I don't really know why they make this change. It's some historical reason. The logarithm is used in the equations involving cell potential. So where we're using natural log in thermodynamics, we're using log for cell potential. And so if you remember, the log it's basically expressing the base of 10 logarithms or log, which is going to change by a factor of, let's write it, yeah. It's basically going to be, the difference is 2.303. Because, and we get that because if we said the natural log of X is equal to the log of X. And if you just put in some number for X, like 10, for instance, to make it easy, and you do the natural log of 10, here's my calculator. 10 natural log is 2.3025 or 2.303, right? And what's the log of 10? It's 1. So if we were to solve for x, we'd end up getting 2.303. All right, that is the relationship between natural log and log. So what does this end up being? This ends up being E cell equals, let's get a different color. Okay, we're saying that this equation here is 8.314 times 298.15 divided by 96,485 coulombs per mole times 2.30, let's circle this, times 2.303, okay? And when you multiply all those together, you get 0.0592 log K. All right? All right. Hopefully that made sense. If not, we can try it again, get like in lecture and lab. All right. So that's how we go from natural log to log of K. And when we do this, we end up getting that the standard cell potential is equal to 0.0592 volts over whatever our moles happen to be, times the log of K. Okay. So with that in mind, try this, okay? Remember, this is the equation to use. What do we have to do for this? Well, we have to, like we've been doing for everything, find the oxidized half reaction and the reduced half reaction. And then from that, we can solve for K. All right, so pause it, give it a shot, and then we'll work on this together. Okay. Okay, so I wrote the reaction up here, and I already went ahead and wrote out what was oxidized and what was reduced, because hopefully you guys have that down now, and I don't need to go through it anymore. So what ends up being oxidized is the copper, and what ends up being reduced is this hydrogen, okay? And when we look up the values, the cell potential, standard cell potential, we get a 0.34 volts for our oxidized reaction and 0.00 volts for our reduced reaction. And hopefully that is familiar, because what is this reaction here? That's She. And that's, as I said earlier, is what we base every other value on. We set that arbitrarily to 0, okay? So if our reaction is E cell equals 0.0592 V over N times the log of K, all we have to do is rearrange it to solve for K, right? So we can say that the log, uh-oh, are you dying on me now? Different color. Let's go back to good old trustworthy blue. All right, you say log of K is equal to the standard cell potential times 0.0592 volts over N. And we just plug in, no, that's not right. I'm going to flip that. Yeah. I gotta flip that to get this by itself. You multiply by N. So yeah, so times N over 0.0592 volts. That looks better. Now what we have to do is plug in for the N and the E cell. Well, what is N? Well, right? These cancel out and they're 2. So that's the moles that we use here. It'll be 2. And what is our E cell? It's the difference of our reduced minus our oxidized, right? Our final minus initial, right? Because oxidized is the anode. That's where the electrons are generated from, and they move to the cathode, which is where it's reduced, all right? And that's the final resting point, or destination. So it's going to be 0 minus 0.34, or just a negative 0.34 V. Okay. And so what we end up with is and then we take the log of each side. We end up with, well, let's not take the log yet. Let's do negative. We end up getting negative 11.48. Okay, so now then to make it just K, to get K by itself, we can say that that is equal to 10 to the negative 11.48, right? And that is equal to 3.3 times 10 to the negative 12. Okay, 3.3 times 10 to the negative 12. And that is how we solve that problem. Okay. And so now this brings us to our last and final derivation, the Nernst equation. And we can use a relationship that we just learned between delta G and our standard cell potential to now get the Nernst equation to solve for Q. Okay, last was K, now we're doing Q. So remember again that come on over here, we have this equation, and previously, last quarter, we said that delta G is equal to the standard delta G, or the delta G of formation, times RT natural log of Q. All right. So what that means is that we can now just pop those together to get this overall equation of delta G, or I'm sorry, what was equal to this right here, the delta G of formation, is now equal to plugging that in for delta G plus RT natural log of Q. Okay, so stare at that for a few seconds just to make sure that sinks in and that makes sense to you guys, how we're getting this equaling this. Okay, by saying that this is equal to this, therefore we plug this in to here, right? Clear. And so if that's the case, next slide, please. Oh, goodness. Last one I did. Oh, we skipped over this one. So here's another, I mean, this is going to be similar basically to the one that I just did. I think this comes from OpenStack. So work on this. If there's any questions, ask me during lecture time. Okay, so now we get to this point. Here we are. So if we divide both sides by the negative moles Faraday, now we get the Nernst equation. So we went from this, okay, and we're dividing both sides by negative NF. So what happens when we do that? Right, if we get rid of this, and we get rid of this, we have this, okay? N and F are now gone. And so, again, we're going to go from natural log to a log. And so now that's going to be the same thing, 2.303 times the gas constant times temperature. And these are going to be standard, right? So it's going to be 298.15 over NF, okay? And so if it's at room temperature, it's going to equal a point, again, the same number, 0.0592 volts. So the equation is going to become this E, or this standard cell potential, minus that number, 0.0592 over N over log Q. Okay. So now you guys should be pretty much masters at oxidized and reduced half reactions and plugging it in and figuring out how to solve for whatever is missing. Here they're asking for the cell potential of this electrochemical reaction, okay, or this electrochemical cell based on these two half reactions. So what I want you to do is I want you to figure this out. Now notice we've given you the concentration here, okay? So you have the concentrations. What else do you need to do? Well, you'll need to assign the oxidation and the reduction reactions. And you'll need to look up the tabulated standard cell potential values. And you'll have to see when you split up these reactions what the coefficient is. Hint, hint, hint. Right here, for the moles of the electrons. And yeah, let's see if you can solve this. And if not, just stay tuned. We'll work on it together in just a minute. Okay, so I've written down the oxidized half reaction that involves the copper. And I've looked up the standard cell potential for that, which is 0.34 volts. And then I've assigned this second reaction as being the reduced reaction. And I've looked up its standard cell potential, 1.68 volts. The next thing we need to do is balance the electrons. Okay, so we have a 3 here and a 2 here. 2 times 3 is 6. So if we multiply everything up here by 3 and everything down here by 2, the electrons will be balanced, right? So I'm just going to write it in quickly. We have this times 3, so that's 3 coppers. And then we have this times 3 copper ions. And then that's going to give us 6 electrons. We multiply everything down here by 2. 4 times 2, that gives us 8 waters. 3 times 2, that balances the electrons, 6 electrons, and then 2 here. Oh, and then don't forget this guy. 4 times 2 is 8. Okay, that's nice. That's going to now, was that right? Was that a 2 or was that a 4? That's a 2. 4. Okay. All right, so then what does that give us overall? Well, that's going to give us, wait a minute, I think that should be an H plus. Sorry, guys. I'm looking over that initial, those reactions they gave us. That's a 4H plus. Okay, so that looks right. Okay, so then now we piece that all together and we get what? We get a 3 Cu plus 2 MnO4 plus 8 H plus, and we can cancel out our electrons, so we don't need to write those in there, yields 3 Cu2 plus 2 MnO2 plus 4H2O. Okay, so this is just kind of really a recap of balancing half reactions. But it's going to be important because it's going to tell us what to use for our N in our equation and how to set up our Q, okay? Because they're not asking for K. In the last equation, they were asking us to find K. Now they're asking us to find the cell potential. And so we got to figure out what Q is, but we can do that because they gave us the concentrations. Okay, so remember, if we look at that initial, those two initial balanced equations that they gave us, they had the concentrations in there, and it was, let's go back to red. Okay, so copper, maybe go back to red. Oh man. is this? Oh yeah, that copper was 0.10 molarity. Okay, and the permanganate was 2.0, and the hydronium ions were 1.0. Okay. Now remember what Q is. It's the concentration of the products over the reactants, right? So it's going to be this. That's a product. Oh, that should be 3. Forgot my 3. Sorry. Okay. There. The concentration of this over this and this. And we have to, of course, take them to the power of their exponents, right? So how can I write this? What do I get rid of? What can I erase? Let's erase this down here, okay? So we say that Q is equal to the concentration of the product, so 3 copper ions. So that was, what was that? That was 0.010 raised to the 3rd, right there, over 2.0 raised to the 2nd, right? And then the last one was, what was that? It was 1.0 raised to the 8th power, right? Because this and this and this is those are the concentrations we were given, right? So that's Q. Now we just need to plug in the other things. The Nernst equation says that it's equal to the log of Q. Okay, so it's the log of all that stuff. And then what else do we have? We have Faraday's constant times, or we have gas law constant times temperature times that 2.03 all over Faraday. And that gives us a 0.0592 volt, right? Follow me so far? Over N. Now, what is N? N here is 6, right? Because that's what we had to get to cancel them out. So it's going to be N is 6. And then what's the last thing we need? We need that those values of the standard cell potential. So final 1.68. Oops, I lost my light, one of my lights. I have a veritable collection of lights to make it bright enough so that you can kind of see the board when it's midnight. Okay, so 1.68 minus 0.34 is 1.34. And that's volts. Okay. And so, and that's actually, let me subtract that. 1.3 volts 1.34 volts minus this, all of this stuff here. Okay. And so what that ends up being is 1.34 volts minus all of this stuff. Okay. That's going to end up being, now I can erase all this. For our Nernst equation, we get equals 1.34 volts minus 0.0592 volts over 6, because that's our moles, times the log of those concentrations that we were given. Okay, so that's going to end up being minus a negative 0.065 volts. Okay, do these calculations, make sure you get that number. Okay, and that your order of operations is all good. And so that ends up being 1.41 volts, because it's minus a negative turns that into a plus. Okay. Whew. Okay. We did it. I think that is it for the lecture. Let me just check and see. Yeah, that's it. Okay. I hope that this all made sense and was fairly straightforward. If not, again, please come see me during lecture or lab and we can chat further. Or if those times don't work, or if you want to just chat via email, that's fine too. So I'll see you guys next time. Bye.